Class, now we'll move to our second topic in solution. We have already covered Raoult's law. Now we are moving to the second topic, solid plus liquid, or to be more particular, NVS plus liquid. What is NVS? NVS is your non-volatile solute. What was volatile substances? Volatile substances which readily goes in vapor state, but non-volatile solute, just opposite, does not evaporate readily. Example, let us take example, sodium chloride, potassium chloride, they are all ionic bonded solute and they never vaporize. So, what are non-volatile solute? Which does not evaporate readily at any given temperature. Example, NaCl and KCl. Since they do not evaporate, therefore their parts, okay, we have taken solute as suffix B. Suffix B. So we can very well write partial pressure of B will be 0 because it is non-volatile solute. Now, before going into detail of topics non-volatile solute plus liquid, we must understand that why non-volatile solute has no vapor pressure of their own and what happens when you dissolve non-volatile solute to any given liquid. Let us take example by this. Class, I have taken water. You all know that water is a volatile liquid. And now I am going to add NaCl to it. Sodium chloride. Sodium chloride is simply your common salt. This is found in your kitchen. And we are all very familiar with NaCl. Now we get a solution over here. Solution of NaCl aqueous, AQ. Now class, question comes in our mind that if we add sodium chloride in water, definitely water is going to be salty. Now the water will be salty everywhere. Either you consider here, everywhere water will be salty, and at the top of the solution, again the water will be salty. So some solute particle has arrived on the surfaces also, because you find as soon as you drink this salty water, you find the water is salty. It means some solute particle has already come on the surface. In class, as you know, they don't have any vapor pressure. They are occupying a surface over here, and we all know that vapor pressure is surface phenomena. So ultimately, the surface area due to this non-volatile solute of liquid decreases, and now we find that vapors coming out are very less. So class, I repeat again, if we add non-volatile solute to any given liquid, not only water, to any given liquid, some solute particles are present on the surface, and they are present on the surfaces, they don't have their own vapor pressure. So ultimately, when we add non-volatile solute, please remember, vapor pressure of solution always decreases. A very important term to be understood here. Whenever we are adding non-volatile solute to any given liquid, vapor pressure of solution always decreases. That is the basic you have to understand before going into the detail of solution of non-volatile solute plus liquid. So class, I repeat again, whenever we add non-volatile solute to any given liquid, vapor pressure of solution always decreases. So class, a new term arrived here that is called colligative properties. So in simple term, what is colligative properties? The colligative properties are the properties which are dependent on number of moles of solute particle. So class, what is colligative property? Okay, we symbolize that Cp. So Cp are dependent on number of moles of solute particle. So I can very well write here colligative properties directly proportional to number of moles of solute. Very, very important thing to be remembered always in the solution chapter. And then class, how many types of colligative properties we are going to study in this topic? I am going to write here types of colligative properties. 4 types. RLOVP, that is relative lowering of vapor pressure. EIVP, elevation in boiling point. Then DIFP, depression in freezing point. And the last one is your osmotic pressure. So these are the 4 colligative properties which we'll be studying in this topic, that is solution of non-volatile solute less liquid. So class, so the topic for the day is RLOVP, that is relative lowering of pressure. Now I am going to rub the board. So today's topic is colligative properties. What was it? NBS plus liquid, and we are going to work on relative lowering of vapor pressure. Class, let us take pure liquid A, volatile solute liquid, giving vapors, let the vapor pressure be PA0. Now let us add non-volatile solute to it, sodium chloride. As I already told you, that vapor pressure of solution will decrease because some solute particle will be on the surface. So let it be PS, vapor pressure of solution. Here it is volatile solution containing NVS plus liquid. So class, as per Rlovp law, PS equals to PA plus PV, but PV equals to 0. Therefore, PS will be equal to PA, but you know PA equal to XA into PA0. Remember Rlovp's law. So we are going to put here PS equal to XA into PA0, but again we know XA plus XB equals to 1. So in place of XA, I can write PS equal to 1 minus XB into PA0. Let us open it. PS equal to PA0 minus XB into PA0. Let us take this thing here and PS there. So we get XB into PA0 equals to PA0 minus PS. A very, very important expression here. Class, again let us come over here. Remember, as we add non-volatile solute to any given liquid, what we studied the vapor pressure of solution, decrease it, but we studied theoretically. Now consider this expression here. This expression is PA0 minus PS. What is PA0? PA0 is vapor pressure of pure liquid A, and what is PS? Vapor pressure of solution. With the help of this expression, we come to know that PA0 is greater than PS. What does it mean? It means vapor pressure of solution is less than vapor pressure of pure liquid A. And theoretically we are proving it. Now it is mathematically proved. Now class, moving further. In the next step, I can write XB equals to PA0 minus PS. Okay, class, nothing more. This was not vapor pressure of pure liquid. This is my vapor pressure of solution. So it can be written as lowering of vapor pressure. How? Let us take an example. Suppose where pressure of liquid A was 100, where pressure of solution is 75. So 100 minus 75 gives you 25. And what is that 25? It is the 25 millimeter mercury pressure. The vapor pressure has been lowered. So PA0 minus PS gives me the expression lowering of vapor pressure. Now in the next step, we are going to divide the lowering of vapor pressure by PA0. So class, if this was my lowering of vapor pressure and this was my original vapor pressure, so lowering of vapor pressure divided by original vapor pressure gives me relative lowering of vapor pressure. Relative lowering of vapor pressure. Let's further open it. PA0 minus PS upon PA0. Mole fraction of B, you all know, number of moles of solute upon number of moles solute plus solvent. Class, dilute, the chapter name is solution, and to be more particular, it is dilute solutions. And in dilute solutions, what we find, number of moles of solute is much less than number of moles of solvent. Therefore, NB is ignored in denominator. So we get final value here, PA0 minus PS upon PA0 equals to NB upon NA. This becomes my expression for relative lowering of vapor pressure. Class, I can repeat again. We have taken a pure liquid A with vapor pressure PA0. We are adding non-volatile solute, example sodium chloride to it. What happens? Vapor pressure of solution decreases, that we already understood. Total vapor pressure is given by PA plus PV, but PV equals to 0, therefore PS equal to PA. But we also know mole fraction whenever it gives value 1. So in place of XA, I can write 1 minus XB. So PS equal to 1 minus XB into PA0. Open it, we get PA0 minus XB into PA0. Next step, we took XB into PA0 here and we took PS here. So we get PA0 minus PS. So PA0 minus PS gives you lowering of vapor pressure. And if you divide by PA0, we get my relative lowering of vapor pressure. Next step, since we are working on dilute solutions, so number of moles of solute is much less than number of moles of solvent. Therefore, NB is ignored in denominator, and finally we get the expression for relative lowering of vapor pressure. Now students, we are going to solve a numerical based on this. And the formula remains question is 6 gram of urea, molecular weight 60, was dissolved in 90 gram H2O if vapor pressure of water, plus again I am giving the value by own, don't quote it, was found to be 100 mmHg. Find PS number 1, number 2 LOVP, lowering of vapor pressure, number 3 relative lowering of vapor pressure RLOVP, and number 4 XB, that is your mole fraction of solute. I repeat the entire thing again. 6 gram of urea, molecular weight 60, was dissolved in 90 gram H2O. If vapor pressure of H2 was 100 mmHg, you are supposed to find out vapor pressure of solution, lowering of vapor pressure, relative lowering of vapor pressure, and mole fraction of solute. So class, let us write down the formula first. PA0 minus PS upon PA0 equals to NB upon NA. PA0 100 mmHg, PS we don't know, again upon 100. Number of moles of solute, weight upon molecular weight. Number of moles of solvent, 90 is the weight and 18 is your molecular weight. Next step, 100 minus PS upon 100 equal to 6 by 60 into 80 goes up by 90. So 10, 5. So 100 minus PS of 100 equals to 1 by 50. 1 by 5 is 0.2. 1 by 50 will be 0.02. So 100 minus PS equals to 0.02 multiplied by 100. Plus, if you multiply it, you get the value 2 here. So 100 minus 2, 100 minus 2 equals to PS. So class, we got vapor pressure of solution 98 mmHg. So you see, previously the vapor pressure was 100 mmHg, but when we dissolve 6 grams of urea in the water, ultimately vapor pressure of the solution decreases, and we got the value 98 mmHg. So that was my answer number 1. Lowering of pressure, PA0 minus PS gives you LOVP. Vapor pressure of liquid minus vapor pressure of solution. Vapor pressure of liquid was 100. Vapor pressure of solution is 98. So that gives you 2 mmHg. I've already told you, never interchange the units of pressure. Then third was RLOVP. We know that PA0 minus PS upon PA0 gives you RLOVP. So this was 2 upon 100. That gives you 0.02. This was answer number 3. And class, we have calculated the value PA0 minus PS upon PA0 equal to 0.02. And remember, this equal to this. So mole fraction of solute is also 0.02. So in this way, numerical on relative lowering of pressure can be solved. So we have taken the very first subtopic of colligative properties, that was your relative lowering of vapor pressure.